Right, so it says that y prime 2x. Okay, I hope everybody can hear me in the Zoom, right? I can't see the chat. Please say something. Minus, yeah, okay, thank you. 3y plus 1. Okay, so now the analytic solution is given here. In the same time, I'm writing on the Zoom y of x 1 on 9 plus 2 on 3 x plus 38 on 9 exponential of minus 3 times x minus 1. Okay, now so part A says that find the local truncation error, truncation error, where if we use the Euler method, forward Euler method, plus h times y prime or f of xy xn plus h squared 2 factorial y double dash c. C should be belongs xn and xn plus h or xn plus 1. Now so for that one we can use, let's go to the Zoom so people can see. So usually so this is local truncation is this one, y double dash c. Okay, so since usually we don't have analytic solution, okay, and we see that so but if we have that, so why not, we can use it, but usually we don't have. Okay, so I want to abuse this situation to write this one definitely. So this will be the first derivative of this one is 38 on 9. The exponential of derivative is itself, but the chain rule tells me that there should be minus 3 derivative of this one. And can I write this x just c and h 2 so derivative of this one again will be 38 on 9, derivative of this one itself c minus 1, and we have another 3, so minus 3 it will be 9. So at the end it will be h squared exponential of minus 3 c minus 1 times 19, part A. So part B says that find, this is the way that there might be some mistake in the solution of this today. Okay, right. Well, my actually recording is coming from my desktop of laptop. Okay, but we will just spend some few times for this question. So then after we will go to the SageMAth. So it will be just through the desktop of my laptop. So sorry people at home if you are watching this video later. Now find the bond for the finding bond for LTE when we calculate y of 0.5 if h is 1/10. Yeah, 0.1, 1/10. It's the another saying. Yeah. So now for this one, h square h2 19 e to the minus 3 c minus 1. C should be belongs to, okay, you will tell me this part. So I wrote this one. So finding bound for the upper bound for the LTE if we want to calculate y of this part, and everything starts from y of 0. And let me see the question again. All right, y of z and y of 1, sorry, y of 1 is 5, and we are going to find, okay, so no one correcting me, so y of 1.5. okay, so we got this one, so we don't have this one. We are going to find this one. So I want you, so still you didn't tell me this one what this is. Okay, so h squared times 19. So instead of h, I will write 0.1 power 2 times 19 exponential of 3 c minus 1. What is this here? This one? 1. Well, not exactly. It should be a little bit over. I said that C lives here. C lives here. Okay. So can you please tell me this one with regarding that C is this one?
H is 0.1 and it's 1.4.
Yes. So 1.4. okay, so exponential is a decreasing function here because in the exponent has got a negative, so this will be negative sign. 0.1 squared times 19 exponential of minus 3 times 1.4 minus 1. In the solution this part has been missed, so but we can put this one, so 19 divided by 100 times exponential of 3. So so this will be, I will put this one instead of 1.4, I will put 1. Okay, 1.1. So this will be 19 on 100. Did you understand it? So C 1.4, and I'm telling that exponential is coming from the top to the down. Okay, as we go to the right, you're right. Okay. And C, the true way to do this one is 1.4 here, but we can, I choose to be this one 1. It's outside of this one, but anyway, the problem has told us to find the upper bound. So I put it 1. Here, 1 minus 1, 0. Question?
And we can select any point between this, between x0 and x plus h.
Oh.
That's why you select 1.
Beg your pardon.
Why you select 1 for C?
Because I'm going to find the upper bound, and if C is, so this function exponential is like this one.
Yeah.
Okay, so this C lives here. So
Yeah.
I choose the 1.4. So this is the problem. This is the answer of my problem. Okay, but because calculating exponential is hard, so I'm coming to say that instead of 1.4, I choose 1. So this will be bigger than this one. Yeah.
But it's saying why can you choose 1? Like, can you choose anything in between 1.4 and
No, then it will be smaller than this.
as is anything smaller than that, but 1 was the easiest to calculate.
Yeah.
Okay.
So what?
Yeah. Because
Yeah.
So
Is that-
we just select 1 to make it easy for us.
Yes.
That's it.
Yeah. Question 3. Question 3. Let's go. Let me. Sharing my desktop. Okay. So find a bound for we did it. Approximate 1.4 using this one, h equals 0.1 and h equals 0.05. So let's go to the SageMath. So what was the thing here? So what I wanna do, I'm just using the SageMath. So let's see. So we got Euler method here prepared. Okay, there's a prepared function, but to be honest, we should implement it. Okay, Euler method, and the problem was like this one here. Here 2x minus 3y plus 1 with this initial condition here. Now 2x minus 3y plus 1 with the initial condition of 1, 5, and h is, now this argument is related to the h, 0.1, and what we want to do is calculating y of 1.5. So here I have this, will it work? Okay, it worked. So we found it 1 point. So let's save somewhere because we need it. Okay, this, and what's the other step? What's the other step? 0.1. Please tell me. So I wanna change. I need to change this one.
0.05.
Excellent. Thank you very much. Okay. So you see that we increase we make the h smaller. Therefore, the steps has been increased to the 10. So the goal is here 1 point. This one. Let me. So here I'm going to save this one. Can I save this one? Okay. Now let's go to the question. Now this is with, so I will remember that this is with a finer step, this is with the lazier step. Now the question tells me that, so we did the approximation. Now it says that D, this is the important part, that's that's the goal of today. So calculate the error in part C and verify the global truncation. So the global truncation, what we have obtained for y of 1.5, we will compare it with the value that we can obtain from analytic solution. So using the analytic solution, let's go to the SageMath again. So the analytic solution. So this is the analytic solution here. Yeah, this one. Do you see the analytic solution? Okay, the highlighted one is the analytic solution, and to obtain the exact solution, I will substitute x by 1.5. Now I've done this one on Monday's tutorial session, so we obtain it here. So we see that this one. Therefore, if I compare this one with the exact solution and the absolute value of the exact solution, the difference of the exact solution, and with the bigger step solution, which was 1.8, therefore we can obtain this one. Let's obtain the difference of the exact solution and the final step. Okay, now you see that this is the, let's go to the solution here. This is the, one of them is E0. We can say that one of them E index E0.1 and one of them is E0.05. So let's go back to the SageMath. So okay, we know that the local truncation in Euler method is OH squared, big O notation of AH squared. Therefore, the global truncation error will be big O notation of H. Now, if we want to divide this one 0.2 with the difference of the exact solution and the final step, this will be H. Now do you see this one 1.9? what we expected is just 2. Well, I think I need to write. So we can do this one. If we, let's go back. Let's wait for something here. Okay, we have this one now. This is OH. We calculated OH for 0.1 and we calculated for the 0. So okay, I think I am now ready to write. Okay, so we obtained this one 0.1. It is we obtain this one, which is 0.2324. We obtained 0.0. I will come back to the screen share. 0.1108. Okay, now what we want to do is this one here. Let's go back here. Okay, so we know that EH is big O notation of H, and from here you know that. So let's assume that EH of 0.1 is something times H, or something times 0.1, and now I divide it by this one by big O notation of E 0.05 something times H, or something times 0.05. So if we cancel the somethings, therefore we will have 2. Okay, are you happy with this? So what we have obtained, so I divided, so in order to to see that the global error truncation is working, we obtained 2 different steps, EH. I divided them and I saw that so in fact different H divided for me, it will be H divided by H. This H, I am sure that you're not confused with this. This H is 0.1, this H is 0.05. So 0.1 divided by 0.05, it will be 2. What we obtained, now let's say goodbye to the here. I'm going just to share now from now laptop. Okay, what we have obtained is this answer, 1.9115. Okay, it's beautiful, yes? Yeah, very close to 2, and I think so. Who is taking the course Civil 2060 here? So Civil 2060 has got some idea about these things, but they're not going to be deep about that. It's numerical methods with the working up the civil engineerings. Yes, please.
Just back on that last notebook.
Notebook is
Yeah, right on Sage.
on Sage, yeah.
Just on the division, where did that second term come from?
Which term?
The division, yeah. So the first term is the error for 0.1.
Yes.
And the second term is 0.05. The error for 0.05.
Yeah, I see. I think this should be this one, and this should be thanks for. I think, do you know, I have obtained it differently here. Okay. Yeah, thank you for correcting. Okay. Do you want me to review this question again?
No, it's around the same percentage of anyway.
Yeah.
Okay. So what you wanna do is to follow for the assignment. What you wanna do, you want to follow this SageMAth week 9. Okay. And also there's a YouTube link for this, and I think since I'm recording today's work, so you will be able to do your assignment, the SageMath part, perfectly. Number 1, if you use improved Euler method instead of Hume's method, you won't get a score. Okay, and I will make an announcement about that as well. So now, so the details that you might need, so is this one list, but we have like reviewed these things like in the first week. So making list in Python or SageMath is comes from this one. Appending to the list is like this one. So if we have this one here, so what do you think if I print this one? PTS 2 3. So if I can append this number to my list. Okay, so
You gotta run the first one into one.
I think PT
The in3 line, the input number 3.
which, so you tell me.
So go to the top line, you can see right there, input 3, and rerun that.
Uh-huh.
Now rerun all the things below it.
Okay, yeah, thank you. Okay, so yeah, and if I do this one, it will be 7. Okay, however, we did this one in the week 1. Okay, now you have week 9 example 2. Can we go to that part maybe? Week 9 module. So use the improved Euler method example 2 to approximate y of 1 for the differential equation. So this is the differential equation. What I've done is this. Y prime, so let's have concentration because you will help me. Y prime x squared divided by y plus 1 plus x cubed. The initial part is this one. So I define the function with this one. So firstly xy, just copy this one from the here, okay? And as I told, I think I told this one on Monday. So xy is just the variables of the polynomial with this line. I mean, this line means xy are the variables of a polynomial of 2 variables with the coefficient of the q. You can use r as well, but it doesn't make any difference. So our function is x squared divided by that one, x squared divided by y times this one, x squared divided by y times 1 plus x cubed. Now here we are going to use improved Euler method. We need to implement it, okay? So this is the list of the solutions or answers that we are going every time add to this list, okay? The variable pt, the pt will be our solution x and y. So pt will be go to inside this pts. Now pt as I said will go to the inside list which we call the PTS. Now here is the sensitive part, okay? So here is this highlighted part is the for loop, okay? The indent or block here shows that PTS1 and PTS2 is outside of the for loop. So range from 1 b minus x divided by h plus 1. Okay, k1, can we go to the notebook? Okay, so y equal, so we are going to here h01 point 0.1, y1 is this one. So x0 is just the initial part. This one is evident what it is. y1 is y0 plus h onto k1 plus k2. Okay, and k1 is the easy one, f of x0 y0. Let's go to the SageMath. So k1 is f of x and y, k2 is the f of x plus h, y plus h times k1. Am I right? Yeah. k2 is x0 plus h, y0 h times k1. y0, okay, y0 plus h times k1. Now here, so with using these two auxiliary functions, this will be y plus y will be this one. I'm writing this one. Okay, here h divided by 2, division is here, k1 plus k2, and every time when I did my job about x equal x0, I will add x equal x plus h. Then after, pt is the vector of x and h, x and y. X and y, and PTS. So then we will add this one to our list of the solutions. Yeah. So now please note that list of the solutions has got x and it has got y. So this is the xy comes from here and here. Okay. So I add this PT to the list of the big list of the solutions, PTS. PT is the just one couple solution, x and y. So I add this every time inside loop to the big list of the solutions, PTS. So PTS now it has xy, 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 xy. So I call PTS1, PTS2. I will use these two lists in order to append, to separate my x's and y's. Okay? Or I in range of the lengths of the PTS, whatever it is, and since I was lazy to think about that, I just wrote lengths of PTS. PTS1, so the first row 0. If it was MATLAB, I was writing 1. Okay? The first what is this? Column. Yeah. The first column I will call them x's or PTS1, and the second one I will put it in the inside PTS2. And after return PTS1, PTS2, then print it. Right. Okay. So can we okay, so what's improved Euler is doing, the arguments are h and the b is the goal. Okay, let's see this one. Can we apply 0.1? What do we wanna do here? Okay, so y2, I think it's going to calculate 1.1, maybe? No, 0.1. Okay, 1, y of 1. With using this one, that's 10 steps. I will call this one 0.1. Okay, so this one is x is 0.1. Okay. 0.1, 0.2, 0.3 x changes. Okay, and the last one should be y of 1. Right? Now, so can we compare our solutions to here? Okay, people in the Zoom, if there is any question, please let me know. Okay, so what's this solution? What's the answer of this question in the book? Right, so this is the answer 1.209172. Can we compare it? Okay, this might be a little bit different, but it's okay. But we believe that our work, oh, okay, this improved boiler is here. 1.209. Yeah, so that's right. Do you have any question about this? Okay, we have x's, we have y's. So we can plot the points. Okay. For example, this one corresponding this one corresponding this one. Okay, so right, so I'll take the improved Euler method here with using 0.1. What I'm gonna do, plotting this one. So this t, as you see that this t is it has two components, and each component has got 10 elements. Okay, so therefore I take the t, the improved Euler, and this I'm going to save this list. So T0 will be this list. Okay, the list of the x, T1i the list of the y's, and 4i, for example, in range 4, I don't know why I did 10, maybe because it was already 0.25, that's why. Okay, then using this one we can start to plot this r, right? So this part, so r will be this T0i. I will separate this. I'm with the here the highlighted r is separating this one, x's and y's. Okay, so that's making the points x, xy, xy, xy. So there are other ways to write these things beautifully. Okay, I didn't optimize the codes, and so list of the plots are okay. So we can get the points here. So these three lines will give us the points. So since I like to plot the solutions, like connect the points together, it will be a right lines, straight lines. So improved Euler, again I'm writing this one, so I'm writing 10 here. In fact, let's do this one differently. 20, so 25, so this will be 4. This might be okay, we will change it later. Let's put this one, let's do this one so you can see that. Okay, perfect. I think I should change this one to 9.
I think the last will be 3.
Yeah, thank you very much. Okay, now this one. Okay, so one time I used h equal to 0.1 and one time I used 0.25. Now let's see another method. Runge kuta. So example 4 of the lecture note week 9. So let's go here. Example 4. So example 4 for this one, it's the same. Okay, it's the same question. Okay, so we can use Runge kuta. So the same story is going on here, except this part will be changed. Okay, in the improved Euler method, we got this loop here. I'm pretty sure that you know that in Runge kuta you will have K1, K2, K3, K4. So here K1, K2, K3, K4. So the rest of the story is the same as the improved Euler method. So Runge kuta, I applied Runge kuta with the 0.21. So the step size of the Runge kuta here is bigger than the improved Euler method, but the solution is 1.2091, which can be the same as the Euler's improved Euler ones. So this means although we have to do more at first, but we can get with the bigger step or less number of the steps, we can get the solutions. Okay, now the same story happens here. This plotting. So plotting that example using different steps, 0.25, 0.1, and this one is the dangerous one, 0.01. Okay, as the step size is going to be smaller, it will be finer and it will close to the exact solution. So now if we have Runge kuta, so for different example, what is this? Question 2 of the tutorial week 9, it's okay. So if you understand one of them, you will be able to plot it. Now another thing, what's the time? Yeah, so the same solution, the same questions here. Okay, what you wanna do is this one. You will use the ODE. I don't know why I don't have here. Okay, you will use the list of the. Okay, let's go back here maybe. Okay, let's go back here. Here now let's go question 2 of the lecture week 8. Question 2. I don't have other to do these things for the SageMAth here. Okay, you need to do this one. So you can use improved Euler method or anything else to do this question. Okay, right? So then after, what you wanna do, let's come here. Okay, this is the Euler method which I used for that one. You happy with this? Yeah, and we use, if you remember, we obtained these ones. Okay, so what we can do is this one, real field Euler method. So this, just copy this one, it's okay. So this part PTS gives us the Euler method, and we can plot the list of the points and list of the lines connecting to each other, connecting the points to each other. And the other thing, we can do different step size. Here is 0.1, and if you remember, we did for 0.05. Now the important thing is you see that with using this function here, plot slope field, okay, you can plot the vector field for your SageMath. Okay, the green one is the smaller step, the red one is the bigger steps. Okay, now let's do another example. So you see that this, we have seen this one question, one of the questions in week 1. This is the y prime highlighted one, y prime equal to sine xy divided by x. Right here. So we have this condition, when x is 1, y is equal 1, and the step size is 0.5. The goal is to calculate y of 5, right? So we use, okay, Euler method, list of the points and lines. These three highlighted lines gives me the points and the lines connecting the points together. Solutions. The second triples, okay, gives me the same things but with the finer step. So this will be 0.2. Now this one, I can, so you should go to the question here. So I defined x variable, x to be variable, okay, and I solved sine of xy with using the ODE, DE solve. You can see DE solve here, DE solve, then you can plot. So Euler method for this function, Euler method for this function with different steps, and this is the analytic solutions which I have obtained with using DE solve. Okay, the materials, the YouTube video and I think video inside Canvas, it does exist. You should go to see how to use DE solve. It's just one line code. Okay, I have obtained this one. Then I decided to plot slope field, which I discussed in the previous question, and plotting now the list of the things, including this P. P is the analytic solution. Analytic solutions. So you see here. Okay, now look at this plot. Okay, the red ones, including the points, they are first Euler method with the step size of 0.5. The second green, which you see that with more numbers of the points, it means with the step size of 0.2, and the blue one is the analytic solution. So in your assignment, I think you should do this one. You should plot this one with different steps, and you see that as more points, you will be close to the analytic solution. Now, so this vector field also good to plot it. I'm not sure if you are asked to do this one. All right. Okay. So today's meeting, it was about calculating the big O notation of the Euler's method. I think you've been asked in your assignment to calculate the global truncation of the big O notation of the improved Euler and Runge-Kutta, and you will do the same job. You will divide different big O notation of different steps together to obtain what you expect. And also the other things that we need to do in the assignment is these things that we reviewed today. If you have a question, please let me know.
Thank you.
Oh, okay, thank you, but that wasn't the question.
So you don't mind if we include a vector field or not? We can add it or not in the assignment.
If I don't remember the assignment, if you are not asked, I don't mind, but it's beautiful.
So we have access to that E09
Huh?
Sage, like notebook that you just showed. Okay.
Yes,
Yeah.
yes.
So how do we find that on Canvas?
Yes.
Can you show me how to find it? How to find it?
Yes, I am able to show that. Assignment. Week 9? Shit. Oh, it's not. Week. Oh no.
The weak ones are the solutions.
Week 8? This one?
Oh, okay.
And oh, okay.
And then
I didn't see this one. Let me see what it is. Oh, right. Okay, you have two useful PDF, which might be more useful. Okay, there are many good files here. So in week 8, if you go to the week 8, can you test it that if you have access to that?
It says 11 a.m.
Well,
Okay.
in 2 minutes.
2 minutes?
Yeah.
Yeah.
Okay. So these two files, it's good. So there is no excuse if you don't try these assignments related to the SageMAth.
So would you prefer it in Sage over straight Python?
You can use Python.
Okay.
Yeah, but if you use prepared function, improve Euler, if you don't implement it, then I will try. I would be unhappy. Okay. No worries. Okay, people in the Zoom meeting, have a good day ahead.
This Zoom today is online.
Yes, just today, because